everyone. Welcome back to our YouTube channel, Becoming a ROS Developer. My name is Rodrigo, and today we have one of our students who has completed the project ROS Basics in 5 days for Python. At the end of our online courses, there is a project you can take and actually implement it on a real robot. So that's what we're going to be seeing here today from Johrdan. So hello, Johrdan, how are you?
Hi. Hello.
Great. I'm excited to see your project. So whenever you want, please share your screen and just show us how you've solved each part of your project, please.
Sure. Can you see my screen?
Yes, I can see it.
Okay, so I will launch the project.
So what are we looking at?
So right now, the robot was in initial position, and then it starts to identify the first wall that it's closer to him, and it starts turning to the right until it finds it. Then you saw that it turned right like 90 degrees, and then it started moving and following the wall that is close to the robot. Right now, it's following the wall.
All right. What is that radians per second I keep seeing on your terminal?
So the radians, that is the velocity, the angular velocity of the robot in the z-axis, and you can see it updating like in almost real time.
I see.
So it will be, the robot will start moving and doing one lap, and it should stop when it returns to its initial position.
Oh, okay, cool.
Which is kind of tricky sometimes because the position is like not really close to the initial position, but let's see.
We can make that bigger if not.
Okay, it stopped.
Awesome. And what's that we see?
So that's the vector or an array with all the points that where the robot crossed or passed by. You have to position in the x and y coordinates and z coordinates too, and that's sent to the terminal when the robot stops. So when it finished the lap.
Awesome, that's amazing. So let me give you a little applause here because when it works the first time, it means that you have put a lot of effort and tested it. So that's really nice to see. So could you please just tell us a little bit on how you've solved each one of these 3 sections?
Sure. So the first section, maybe I can put here the code editor. So yeah, the project consisted in practically 3 parts, doing the while following, the wall finder, and lastly the odom recorder. So first I started with the full following. I started doing this without the multi-threading, but I noticed that the multi-threading was the most important part for all the codes. So I had to use it compulsorily. And I made this using first I started coding the timer callback, which is the code that executes every certain time. In this case, I execute the timer callback every, let's see, every 0.5 seconds. And this is the part where, or the logic of the code, where it says that if the distance to the wall is minus or less than this value, or if it's close or is it greater than 10, that means that it should turn like this amount. Of course, this amount is like programmable. I tested it. I could change it so that it can or that it could follow the path correctly or the wall without touching it, because you have to test it with the velocity that you have. So if it's close to the wall, it should go straight. This means zero angular velocity. If it goes away from the wall, then it should turn right so that it approaches the wall and goes back to following. And if it's too close, then you should go away. And this is the part of the negative velocity. And yeah, this is the main logic of the ball following. Of course, if it's too far away, it should have a big angular velocity, and you can see that when it goes to the corners, so that the angular velocity becomes greater. In this case, I put it like 0.55, and this happens when the wall or when the sensor, the front sensor, detects a wall, so it's about to crash. So the angular velocity has to be greater.
Right.
And that's this code. So yeah, that's in summary the code for the wall following. And then I started doing the wall finder. So for the wall finder, I used 3 callback groups. I also used multi-threading, of course. And in this case, I used the laser callback and the timer callback. So I noticed that for the readings of the laser callback, there's like different values in simulation and in real world. So for the simulation, the values for the array or the value of the arrays should be 0. But when you are using the robot, like the real robot, you have to change it to 180. I think it's turned like 180 degrees. So I had to change those values when I tried to simulate the robot.
Yeah.
And then I started using the timer callback after I solved this part. So this is the logic. So basically, this is to measure or to find the next wall closer to him. So when it starts in a certain position, it first detects what's the wall closer to him. Then when it detects the wall closer to him, which is this part, then it starts to turn around to the right, and it detects, or it stops when the front sensor detects the wall. And this is the part of the moving to the right. And when it detects that the front door or the front sensor is aligned with the wall closer to him, then it stops and it goes around 90 degrees for a certain time. And then it starts moving to like with an velocity in the x direction. And of course, this is the main logic that I put it in the timer callback. But in the when you call this code, it does not stop until it is done. So it's until the last part or until the code is done, it will be the timer callback will be repeated. When it goes like one lap, when the lap finishes, then it will get out of the while code or the while loop, and the code will end. And then that's the answer you see here, that or up there, that the wall was found and it was in the response.
Mm-hmm.
And lastly, the odom recorder. For this, I also used multi-threading. In this case, I used 2. And I used it as an action server to call the odom record. And this is to measure the X and Y position of the robot while the robot is moving. So I first detect the first position, so that it detects, so it saves the first position where the robot was. And this is helpful to see when the robot finishes the lap. So this is the first part of the code. And then I wait 0.5 seconds, because otherwise, as soon as the robot moves, it will detect that it's close to the initial position, and it will stop, and it won't work properly. So I wait like a few seconds or 0.5 seconds, and then it starts moving. And then this is the main logic of the code. So it keeps the record of the last odom reading, which in this case is the X and Y position. And it measures also the total distance that it has been following, in this case, the real robot. And it keeps updating this as a feedback, as you can see here, because this is the feedback that is shown in the terminal. And then when it detects that the position of the robot is close to the initial position, so that means when the lap finishes, then it will break, and it will send like a succeed, or it calls this succeed callback of the goal of the action server. And it will also print the result of all the records or all the positions where the robot was, and this is sent as a result of the call. And yes, of course, to finish the code, I had to shut down the node so that it stops sending messages to the terminal. And yeah, that was the 3 parts of the code for this project.
Awesome. Great. Thank you, Johrdan. Again, the applause here. Very nice project. Very straightforward. And what I like the best is that you went through the code really understanding what was happening. So that means you took a lot of time to figure this out. So let me ask you a couple of questions that I thought were interesting, if that's okay with you.
Sure.
So the first one here to not forget is that you actually call the shutdown of RCL-Pi shutdown here in the Odom recorder, correct? At the bottom there?
Yes.
And there. At the end, right? Okay.
At the end.
Does that actually kill the node on the other side? So right now you haven't done anything to the terminal or the program. So if we go to the if we go to the terminal,
yes,
and so let's check another terminal. Let's do a ROS2 node list. Why do I say this? I think there's a problem with this function, with this method actually.
Okay, let's see.
Yeah, you see it's still there.
Okay, it's still there.
And I thought it was strange because there was this we have a forum, right? You might have actually seen it before. It's that green question mark on the bottom right. And one guy was asking about a shutdown hook in ROS2. And it's like, how do I kill a node when I'm done with it? And without, having ugly, because you could set up like an ugly, not graceful exit somehow, right? You could just kill it somehow. But you, in theory, you're supposed to be able to do it with RCL-Pi.shutdown, right?
Yes.
But this led me like in a rabbit hole that ended up in the conclusion that this function is not actually, there's something in the code of RCL-Pi that is incorrect. So that's why I was like, maybe it's not killed and you think it's done, it's been killed. So just keep that in mind because that will happen a bunch of times. And if you're, if you're expecting that to die, I wouldn't rely on that. Just do it ugly. You can do it with an SH script. You can call with OS with Python. You can call like an external thing that kills everything, something like that.
To be sure.
Just to be sure, yeah. And for a graceful exit, I don't know. I can't. I don't have the answer for that yet. So hopefully in the future. So that's one thing. And
interesting.
Another thing I noticed, I just want to clarify on it. You have the wall server, right? The one that finds the wall. So if I understood correctly, the service server callback is basically just a flag setting, right? And where you do everything is in the timer callback?
Exactly, yes.
That's interesting.
Yes, I noticed that it was, or for me, that was the way it worked because when I tried to do it in the main callback, I had problems with the readings of the sensor. So it was not reading the sensors properly. I'm not sure really why, but when I used the timer callback, the laser sensors are actually updating correctly, and then it worked for me. So that's why I used the timer callback instead of the callback function directly from the action or from the server.
Hey, that's good. That's if it does. I thought it was interesting. It was really nice, elegant for the callback. You just set a flag and let the timer do its thing. That's great.
Yes.
That's great. And then the last question I had was basically like a mental exercise, sort of. You mentioned you were worried in the beginning about the robot not stopping, basically. And I said, well, you can make the radius of that initial position area bigger.
That'd be great. Yes.
Right? How would you do that in a better way? Can you think of a way to basically not be worried that it's going to not stop?
Maybe I would try like experimenting with the timer callback period. So make it a little bit a bit few or like less seconds, like maybe 0.2, 0.1, because it updates every 0.5 seconds in this case. So maybe that's a problem.
Faster.
A bit faster. But I didn't use it like 0.2 or 0.1 because I was worried that maybe the response of the robot was not quick enough and I would have problems with the main code. So I kept the 0.5 seconds like with that value, and I tried using a bigger radius. And in this case, the exercise asked for 0.05 as the radius, but I tried like 0.08.
I keep meaning to change that because it doesn't really matter at the end of the day, and that complicates things. Yes, so you could definitely do that. And another two things you could try and do is make the movement of the robot smoother, which would mean,
yes.
This is beyond the scope of the project, but just so you know, like you would add like a controller or something to make sure it's straighter, the movement, or a simpler version to just use distance traveled, right? So, but that would mean it would be different between if the movement is really squiggly, snake-like, or very straight.
Exactly. Yes.
All right. Awesome, Johrdan. So those are all the questions I have. I just want to congratulate you one more time for a great and efficient project.
Thank you so much. It was really fun to do this project. I think I learned a lot from the basics. And as soon as I have time, I will go on with the other courses.
Awesome. That sounds great. We're excited to see what you do there. And to everyone else that is watching Johrdan here, this is what you can do after you take our courses that offer a certificate. You can apply it on a real robot, do a project, and come present it with us. So I invite everyone to do what Johrdan did here. So thank you so much, Johrdan, and see you around. All right?
Thank you so much.
Okay, bye. Guys, we'll see you next time. Bye-bye. All right, cool. We are done.